Welcome back to my YouTube channel. Today's LeetCode DCC question is greatest common divisor traversal. Let's read the question. You are given a zero index integer array nums and you are allowed to traverse between its indices. You can traverse between index I and index j, I not equal to j, if and only if GCD of nums I, nums j is greater than 1. Where GCD is the greatest common divisor. And our task is to determine if for every pair of indices I and j in nums where I less than j, there exists a sequence of traversals that can take us from I to j. Return true if it is possible to traverse between all such pair of indices or false otherwise. So what question is saying? So we will given an array of numbers, and for every pair of indices I less than j, we have to find whether there exists any path or not. For example, this is I and this is j. So we have to find whether there exists any path between I and j. For that, the path can be a direct path or an indirect path. For example, we can jump to indices this one, and from here we can jump to j. So path can be direct as well as indirect. But the path to be a valid for every jump, for every pair of jump, we have to make sure the GCD of the numbers, GCD of number 1, number 2 is always greater than 1. That means if we consider an example, suppose we have three numbers and index is 0, 1 and 2. And suppose if we want to jump from index 0 to 1, since 0 is less than 1, so this is a valid pair for which we need to find a path. So for that, either we can find a direct path from 0 to 1, or we can find an indirect path from 0 to 2 and then 1. So both paths can be valid only if the GCD of 0 and 1, GCD of this 0 and 1, number at 0 and number at 1 is greater than 1 for this path to be a valid. And for this path to be a valid, GCD of a number at index 0 and a number at index 2 should be greater than 1, and GCD of number at index 2 and index 1 should be greater than 1. So for this path to be a valid, both the GCDs should be greater than 1. So in this way, we have to find for every pair such that index ith index is less than jth index. So we have to find the path. So if there exists a path for all the pairs, then we have to return true. If there is any such pair for which we don't have a path, then in that case, we have to return false. So let's take an example to analyze. For example, the nums given is 2, 3, 6. The index will be 0, 1, and 2. So valid pairs will be 0 to 1 since 0 is less than 1, 0 to 2 since 0 is less than 2, and 1 to 2 since 1 is less than 2. Now we have to find at least one path for this pair, and this pair. So let's see. For 0 and 1. So we can see the number at 0 is 2, number at 1 is 3, and GCD of both these number is 1. That means we can't jump from index 0 to 1. That is, there is no direct path between 0 and 1. Let's see if there is any indirect path. For an indirect path, so let's see if GCD of index number at index 0, that is 2, and number at index 2, that is 6, is greater than 1 or not. So since it is greater than 1, as the GCD of 2 and 6 is 2, that means we can jump from index 0 to 2. Now let's see whether we can jump from index 2 to 1. So number at index 2 is 6 and numbers 1 is 3 and GCD is 3. Since it is greater than 1, so we can jump from 6 to 3. That means we have a path from 0 to 1. Now for 0 to 2. So we have seen like there is a path from 0 to 2 since GCD of 2 to 6 is greater than 1. So we have seen there is a path from 0 to 2 also. And for a path from 1 to 2, since GCD of number at index 1 is 3 and number at index 2 is 6, and since GCD is equal to 3, which is greater than 1, so there is a path between 1 and 2 also. Since we have the paths between all pair of vertices indices, so we have to return true. So how we can approach this question? I hope we have understood the problem statement. Now we can see the greatest common divisor should be greater than 1. So if the vector size given is 1, so if we have only one number, in that case, number of pairs formed will be 0. That means we don't need to check any path. In that case, the answer will always be true. That means if length is 1, we are not worried. So in that case, we have to return true. Now, one more case is if we know the GCD and GCD of 1 with any number will always be 1. So can we say if we have a vector or we can say nums size greater than 1 and there exists at least one once, in that case we will not find a path between that one and any other integer, since the GCD of 1 with any number will always be 1, which will violate this condition. So can we say if the vector size is greater than 1 and there exists a number 1, it will always return false? Now, so we have seen these two base cases. Now, when we talk about GCD, so for every even number, if we see for every even number like 2, 4, 6, like this, if we find the GCD between any two even numbers, it will always be greater than equal to 2. So in case of events, we are not worried about the GCD. It will always be greater than 2. But in case of odd number, we are worried. For example, if we have 3, 5, GCD will be 1. If we have 3, 6 is not odd number. If 3 and 7, it will be 1. 3 and 9, it is not 1. It is greater than 1, which is 3. So if we see this case, and this case, so in this is not common pair. So these two numbers are prime numbers, and a pair of prime numbers whose GCD is 1, we call it as co-prime. In this also we can see 3 and 7 are prime number, and pair of prime numbers whose GCD is 1 is called co-prime. And in this we can see 3 is prime but 9 is not prime. So in this case the GCD is not equal to 1. So, so from this we can see we are more worried about co-prime pair. For such pairs which are co-prime, so in that case there is a probability we will get co-prime pairs and the GCD will be 1. So in that case we will not find a direct path between 3 and 5. So let's see this prime numbers. So we have a prime numbers like 2, 3, 5, 7, 9, 11, 13, like this. And also, can we say can be any number can be represented in a form of prime factors. That means we can represent any number in the multiplicative form of this prime numbers. For example, if we want 2, we can write 2. If we want 3, we can write 3. If we want 4, we can write 2 to the power 2. That means 2 times 2, and both are prime. If we want 5, we can write 5 like this. If we want 6, we can write in the form of 2 into 3. And we can see 2 and 3 are prime. If we want 7, we can write 7. If we want 8, we can write 2 into 2 into 2 like this. If we want 9, we can write 3 into 3. So that means we can represent any number in the form of prime factors, right? Let use this information to reach the solution. So suppose we have given a vector nums such that in this vector, every number in this vector is divisible by 2. Every number is divisible by 2. Since every number is divisible by 2 and we find the GCD of any two numbers, so can we say the GCD of any two numbers will be at least 2. Similarly, suppose we have given a vector and every number is divisible by 3. In this also, can we say if we can find a path between any pair of indices, since GCD of any two numbers will always be greater than 3. Like this, can we say we can from this numbers nums, we can form a group of numbers which are only divisible by 2, which we can form a number which are only divisible by 3, we can form a number which are only divisible by 5. So, and in this group, we can say if there are any numbers, we can find a path between any two numbers. And inside this also, we can find a path between any two numbers. And inside this also, we can find a path between any two numbers. But now, can we say we can find a path between this set of number as well as this set of number? Find a path between this. For example, we have a number 2 here and number 3 here. So we can't find a path between 2 and 3 directly, right? Because GCD will be 1. For that, we need a connector. We need a third number which will act as a bridge between 2 and 3. Or we can say this number as a connector. We need a connector that connects 2 and 3. And a number which connects 2 and 3 must be divisible by 2 as well as divisible by 3. That means, can we say the prime factor of that number must contain 2 as well as 3? In that case, we will form a bridge between a set of number 2 and 3. So if there exists any number which are divisible by 2 as well as 3, or in other words, we can say if there exists any number whose prime factors contains 2 as well as 3, in that case, any number can first jump to this number, and from here it can jump to this number. That means individually, this number will form a group and this number forms a group. And now any number from these groups can find a path to this group if we have this connector. Now, for example, for 3 and 5. For 3 and 5 also, if we see the GCD of 3 and 5 is 1. So we can't find a path directly from 3 to 5. For this also, we need a connector whose prime factors includes 3 and 5. So if we have such numbers, for example, here we have a number like 15. Since 15 is divisible by 3 as well as 5, or we can say prime factor of 15 includes 3 and 5. In that case, any number from this group can first jump to 15, and then from this 15 we can jump to any number to this group. So if we have a connector, that means we can jump from any number from this group to this group. Now let's see, we have a number 30. If we see a prime factor of this number is 2, 3, 5, right? So can we say we can use this number as a connector to form a bridge between 2 and 3, as well as 2 and 5, as well as 3 and 5? We can say it, right? So our problems boils down from this statement to find a connector. So we can say if there exists such numbers, in that case 2, 3, 5, any numbers divisible by 2 3, 5 can find a path in between them if we have a connector like 30. So can we say if we can able to form a group of numbers which are divisible by the prime numbers like 2, 3, 5, 7. Suppose these numbers have a prime factors 2, 3, 5, 7, and if we find a bridge or a connector that form have a prime factors like 2, 3, 5, 2, 3, 5, 7 in them, that means any number from this subset can jump to any number in other subsets. Let's draw and see. Let's take an example to see this. Suppose there is an example of 4, 3, 12, and 8. Now we will see the prime factors of 4. Prime factors of 4 are 2, comma. That means 4 belongs to a group 2. Now 3. The prime factors of 3 is 3. Now in one group we have 2. In another group we have 3. Now next number is 12. So for 12, the prime factors are 2, 3, and 2. That means this number can act as a connector between this 2 and 3. So we can merge these two groups of numbers into one. Now we can write these two groups in a single group since we have seen that there exists any number which can act as a connector between 2 and 3. So now we can write all the numbers which are divisible by 2 and 3 in one group. Now we will see 8. Prime factors of 8 are 2, 2, and 2. That means it belongs to this group only, 8. So since after since for all this number we have formed only one group, that means any number can jump from any number. So in this case we will return true. Let's take one more example. So we have 3, 9, and 5. So prime factor of 3 is 3. So we have one group which contains 3. Now we see 9. So prime factors of 9 is 3 and 3. That means 9 is also inside this group which have a prime factor of 3. Now we see 5. Prime factor of 5 is 5. So we can't put 5 inside this group since this group represents the prime factor for 3. Now for 5, we have 5. Now at the end of 3, 9, and 5, we can see we are left with two groups. So in this case, we can say there are some subsets or some pairs of indices, some subset or some pair of indices for which we don't have any path. There don't exist a path. In that case, we have to return false. Since we need to merge the groups, the best data structure we can use is disjoint set. And we are using the prime numbers. So efficiently calculating the prime factors of a number, we can use a sieve method in which we pre-calculate the prime numbers, recalculate the prime numbers, and we can use it for all the numbers in the vector. So using this two technique, we can try to solve this question. Let's try to code. So we have said like we will be using disjoint set. So first we will create a disjoint set. And for this, we will create a vector rank and vector parent. Now we will have a functions. First we will have a method, takes the size of the disjoint set. Now we will resize this rank as well as we will resize the parent. In the beginning, parent of every indices will be itself. Now we will create a function to find the parent. If parent of v else we will return the parent of, we will update the parent while finding the ultimate parent of that number. Now we will do a union, but it will take two arguments, this u and v. Parent of u will be v, parent of v. Now if parent of u equal to parent of v, we will simply return, we will not do anything else. We will see the rank. If rank of parent u is equal to rank of parent v, we will make the parent of any one of them. Let's assume parent of pu will be pv, and in that case, we will update the rank of parent pv plus equal to 1. Else, if if rank of pu is greater than rank of pv, then we will join PV in PU. In that case, parent of PV will be PU. Else, parent of PU will be PV. So this is the basic format of the disjoint set. So we have written this. Now, since we have to deal with the prime numbers and to use this prime number efficiently, we will pre-calculate prime numbers. For that, let's define the maximum size or the prime number still which we need to find. Now, SPF will be an array which will contain the smallest prime factor of each numbers. Now we will create a function sieve inside this. So for 1, the prime factor will be 1. Now from 2 onwards, we know that for every even number, I equal to 2, I less than max and I plus equal to 2. For every even number, smallest prime factor of I is 2. And in the beginning, we can initialize the prime factor of each number with itself from 2 to max, and we can write the smallest prime factor of I is I. Now we will iterate the odd occurrences, odd numbers, and we will update the smallest prime factor of each number. I less than max and I plus plus. If SPF of I is equal to I, that means this is the smallest prime factor of that number, and we have not updated with any of the small number. So in that case, all the divisible of this number will be the smallest prime factor of all the numbers divisible by this I will be I. In that case, j less than max and j plus plus j plus equal to I. Since we need to find the factors of I, for every factors of I, SPF of j will be if SPF of j is equal to j, then we will update SPF of j with I. So in this way, we can calculate the smallest prime factor of all the numbers. Now we will create another function which will return us the distinct prime factors of all the number. Get distinct prime factors. So suppose we receive a number x. In that case, we will, for create a distinct prime factor, we will use a set distinct prime factors dfs distinct factor. Now y x is not equal to 1, we will push the smallest prime factor inside the dfs dot insert smallest prime factor of x and update x with the SPF of x. and then we can return the vector dfs dot begin. So in this way, so this function will help us to get the prime factors of all the numbers. Now we will see the given function. So inside this, so we first we will find the size of this vector. So what is the base condition? Suppose if the size of this vector is 1, in that case the answer will always be true. So if n is equal to 1, then we will always return true. And if it is greater than true, what we are going to do, we will iterate the vector and see if if this number is 1, in that case we will return false, because we have seen if the size is greater than 1, that means if we have more than one number, and if any of the number is 1, then we can't find any path between these two numbers, since the GCD will always be 1. So these two are the base conditions. Now we will create a disjoint set with size max n, and we will call a sieve method to pre-calculate the smallest prime factor of all the numbers. Now we will create a set which will stores the distinct prime number used. That means in this vector we will see what are the prime factors that are involved. So suppose we have 2 and 6. So if we have this number in this array, then the prime numbers which are involved in 2 and 6 are 2, and for this is 2 and 3. That means only 2 and 3 are involved. So we are worried about only 2 and 3, whether they are in same subset or not. So we are not worried about 5 or 7 or 11. That means we are not worried about all the prime numbers. We are worried about only those prime numbers which are involved, or we can say which are the prime factors of these numbers. So we are worried about only those numbers. So in that case, we have to store which are the prime numbers which are involved. So we can write distinct prime used. Now we will iterate each number. Each number, and inside this we will receive the distinct prime factor of the number by calling the function distinct. Let's copy it. Get distinct prime factors. We will pass nums of I. So it will return a vector which contains the distinct prime numbers. Now we will form if now we will merge. So, so now we will disjoint set the union by rank of distinct prime factors of I minus 1, j minus 1, comma, prime factor of j. So what we are doing in this for loop? So suppose we have a number 12 and we have called this distinct prime factor. So it will return us 2 and 3. Or let's suppose 2 and 3. Or let's suppose we have 30. So if we will call distinct prime factor, in this case, it will return us 2, 3, and 5. So there is a number which can act as a connector between 2, 3, and 5. That means we have to merge all the numbers 2, 3, and 5 into one group. And to merge this number into one group, can we say we can do a union of 2 and 3, adjacent number 2 and 3, and then 3 to 5. Similarly, if we have more number like 7, then we can do a union of these two number. In this way, we can merge, form a group of all the numbers into one group. So that's what we are doing here. So first we will find the prime factor, distinct prime, and then we will do a union one by one. First 2, 3, then 3, 5, and then 5, 7. Like this. So that's what this for loop is doing. In this way, we will form a group. So after forming a group, what we will do, we will iterate the distinct prime factors, and inside the distinct prime factors, inside this distinct prime used, we will insert. Since in this vector we have the prime factors of this number, that means these are the prime numbers which are used till now. So we will insert this numbers inside this distinct prime used. So we will insert now. So inside this for loop, we will find the prime factors of each number. Then we will do a union by rank, which means we will all the numbers acting as a connector. And then we will store all the prime numbers which are used. Now we will see the parent of each prime numbers. That means we will find in this, we will find the distinct parents of each prime numbers which are being used. So means auto IP, we will, these are the prime numbers which are used. So inside this, we will first find the, we will push the parent of all these prime numbers inside this. Inside this, we will insert disjoint set dot find parent this numbers, prime numbers. So once we have the distinct prime numbers with us, we will see now if we can we say if the distinct parent size is greater than 1, that means we have two subgroups prime numbers. So there is a group of one prime number, there is a group of another prime number, and there is no connector between these two groups. If we have distinct prime numbers greater than 1, so in that case we will return false. And if the size of this distinct prime is 1, that means we have only one group. That means we can jump from any numbers to any number inside this group. So in that case, we will return true. So if size of distinct parent is greater than 1, that means we have to return false, else we can return true. I hope the solution is clear. Let's try to run the solution. Okay, there is an completion error. Okay, yes. Semicolon. Since all the test case has been accepted, now we will try to submit the solution. So our solution has been accepted. So there are other approaches also, like since we have used the disjoint sets here to find the groups, we can use a graph also. So if we form a graph, of these prime numbers and we have more than one components, that means there are some subsets of numbers which don't have a path between them. So suppose we form a graph like this, right? And there is like this. So in this graph, we can say that we have two components, component one, component two. So we don't have a path between any of this numbers with this number. So in that case, we can return false. So we can use this approach also, and we can use disjoint set always. Disjoint set also. So choice is yours. I hope my solution is clear to all. Meet you in the next video. Thank you.